At the end of the 19th century, the world of physics stood on the edge of both triumph and crisis. Scientists believed that they had uncovered nearly all the secrets of the natural universe. The great equations of Newton had described motion and gravity with unmatched precision. Maxwell's theory of electromagnetism had united light, electricity, and magnetism into one majestic framework. The universe seemed orderly, predictable, and beautifully complete. Many physicists of that age began to think that their discipline was almost finished, that only a few minor details remained to be solved. Yet beneath that surface of confidence, a single unsolved riddle was quietly growing, threatening to unravel everything they believed. It was the problem of how matter gives off light, the mystery of blackbody radiation. Imagine a piece of iron being heated in a forge. As it warms, its color changes from dark red to orange, then yellow, and finally to a brilliant white glow. That simple transformation, so ordinary in a blacksmith's shop, concealed within it a question that classical physics could not answer. Why did objects emit light differently at different temperatures? Why was there a precise pattern in the spectrum of light they released? The more physicists studied it, the more this humble phenomenon exposed the cracks in their cherished theories. They called it the problem of the blackbody, an idealized object that absorbs and emits all possible frequencies of radiation. It became a laboratory for testing the limits of physics itself. Throughout the late 1800s, researchers across Europe, from Berlin to London, were measuring how the intensity of light emitted by a heated object changed with wavelength. They plotted beautiful, smooth curves, showing that every temperature had its own distinctive pattern. At lower temperatures, the glow peaked in the red or infrared region. As the temperature increased, the peak shifted toward blue and violet, with the intensity spreading across the visible and invisible parts of the spectrum. The data were precise, reproducible, and elegant, yet utterly mysterious when scientists tried to explain these curves using the known laws of thermodynamics and electromagnetism. Their calculations diverged into nonsense. According to classical physics, as formulated by Lord Rayleigh and James Jeans, light waves of shorter wavelength should contribute more and more energy as frequency increases. The result was catastrophic. At ultraviolet wavelengths, the predicted energy went to infinity. This impossible conclusion was mockingly called the ultraviolet catastrophe. It meant that every object, no matter how small or cold, should emit infinite energy, something obviously false. The equations were betraying the very reality they were supposed to describe. It was as though nature had placed a wall between human logic and her hidden structure in lecture halls and laboratories. The frustration was palpable. Some tried to modify Maxwell's equations. Others adjusted the assumptions of thermodynamics or imagined strange new properties of matter. Yet no one could reconcile theory with experiment. The blackbody problem became more than a technical puzzle. It became a philosophical wound. How could the same laws that explain the orbit of planets and the reflection of light fail so completely when describing the gentle glow of a heated piece of metal? The answer, though no one yet realized it, would require a total reimagining of energy itself. At the University of Berlin, one man was watching these developments with particular interest. Max Planck, a modest and deeply thoughtful German physicist, was not seeking to overthrow the laws of physics. He revered them. He believed in the harmony of natural law, in the idea that mathematics could reveal the unity of the cosmos. To Planck, the failure of classical physics was not a reason to discard it, but a challenge to refine it. The blackbody problem, in his eyes, was a stubborn puzzle whose solution must lie hidden in the existing framework. If only he could find the right key. Planck was a theorist of unusual patience. He was not driven by fame or fortune, but by a nearly spiritual faith in the order of nature. Each day he would walk through the streets of Berlin to his study at the Physikalische Technische Reichsanstalt, where meticulous experimental data on radiation spectra were being gathered. Those measurements, especially the work of Heinrich Rubens and Ferdinand Kurlbaum, provided him with precise curves showing how the intensity of emitted light varied with wavelength at different temperatures. Planck examined those graphs obsessively. They were not abstract lines to him, but whispers from nature, hints of an undiscovered law beneath the chaos. He began his task as a mathematician, not as a revolutionary. He wanted to find a formula that could fit the experimental data, something that would elegantly connect energy, frequency, and temperature. He tried every classical method, using the well-established theories of thermodynamics and electromagnetism. None worked. The equations either broke down or diverged to infinity at short wavelengths. He refined them, adjusted constants, rechecked assumptions, but the result was always the same. Nature refused to be tamed by the old mathematics. To understand why this was such a crisis, one must imagine the mindset of scientists at that time. They saw energy as continuous, like water flowing smoothly through a stream. Light, according to Maxwell, was a wave, and waves could have any frequency or amplitude. There was no reason to think that energy itself could be granular or discontinuous. The idea that energy might come in discrete pieces would have seemed absurd, even heretical. The continuity of nature was a sacred principle. Yet, the blackbody radiation curves stubbornly refused to fit that view. At low frequencies, classical theory matched reality fairly well, but as frequency rose, theory predicted an explosion of energy that did not exist. Something in the foundation was wrong. In experimental halls across Europe, scientists kept collecting more data, hoping perhaps the theory would someday catch up. The glowing filaments of early lamps, the heated cavities of furnaces, and even the faint light of stars were studied with increasing precision. Every new observation reinforced the same truth. Classical physics was breaking down. In 1895, Wilhelm Wien proposed an empirical formula that seemed to fit part of the curve, but it failed at longer wavelengths. His equation worked beautifully for high-frequency radiation, but collapsed in the infrared region. A few years later, Rayleigh and Jeans derived another expression using statistical mechanics, but theirs failed at the opposite end, diverging disastrously in the ultraviolet. The blackbody curve seemed to mock human logic, rewarding one approach only to crush another. Planck watched all this unfold with a mix of admiration and quiet dissatisfaction. He respected Wien's brilliance, but sensed that his equation, though elegant, was incomplete. Planck believed that nature would never behave inconsistently. The flaw had to be in human understanding. He decided to derive the radiation law from first principles. To do this, he began with the concept of oscillators, tiny hypothetical charges that could vibrate and emit electromagnetic waves. In his imagination, the walls of a blackbody cavity were filled with countless such oscillators, each radiating and absorbing light at specific frequencies. If he could describe how these oscillators distributed energy, he might unlock the mystery of the entire spectrum. Day after day, he wrote equations, erasing and rewriting, testing the boundaries of thermodynamics. The mathematics became more tangled, the assumptions more daring. Still, he refused to abandon the continuity of energy. Then, one evening in 1900, after yet another long session with Rubens's experimental data, he noticed something extraordinary. When he tried a new, purely mathematical formula, one that combined elements of Wien's and Rayleigh's laws, the result matched the data perfectly across all wavelengths. For the first time, a single equation described the behavior of blackbody radiation at every temperature and frequency. It was a moment of quiet triumph, but it raised a deeper question. What physical principle could possibly justify this formula? Planck knew that mathematical coincidences were not enough. Nature demanded explanation, not convenience. He began to analyze what assumptions were necessary to derive his new law from fundamental principles. As he delved deeper, he realized that he would have to abandon one of the most cherished beliefs in physics, that energy is continuous. To make the equation work, energy exchange between matter and radiation had to occur in finite discrete amounts, as if nature were counting each act of emission and absorption one by one. This was not merely a mathematical trick. It was a profound shift in the way reality itself was understood. But in 1900, Planck was not yet ready to embrace that interpretation. To him, it was a desperate measure, a last resort to fit the data. He introduced a constant, now called Planck's constant, to express the size of these energy packets, which he called quanta. The value was astonishingly small, about 6.626 x 1 34 joule seconds, but it carried deep significance. It implied that the microscopic world of atoms and radiation was governed by steps too tiny for human senses to perceive, but too fundamental to ignore. Before this revelation, the world of physics had believed it understood light completely. The wave theory, born from the work of Huygens and perfected by Maxwell, had triumphed over Newton's old particle view. Light was seen as a continuous oscillation spreading smoothly through the ether. The idea that light might also have a discrete, particle-like nature seemed impossible. Yet the Blackbody problem was exposing the limits of that faith. Nature was whispering that energy itself was quantized long before anyone dared to hear it. To the scientists of the late 19th century, this whisper was unsettling. The beauty of classical physics lay in its predictability, in the idea that if you knew the initial conditions of any system, you could calculate its future forever. The planets moved in perfect ellipses, pendulums swung in predictable arcs, but the Blackbody radiation curve refused to obey such deterministic logic. It suggested that there was a hidden granularity in the fabric of energy, a mystery too small for human eyes but large enough to shatter the foundations of physics. As Planck worked in his quiet study, the world outside was entering a new century. Steam engines powered factories, telegraphs linked continents, and electric lamps illuminated cities for the first time. Humanity believed it had mastered light. Yet, in the tiny flicker of that artificial glow lay a puzzle no one could solve. The same light that guided civilization forward was also guarding the key to an unseen realm, a realm where the old rules no longer applied. For Planck, this paradox was both torment and inspiration. He later recalled how he felt like a man who had stumbled into unknown territory, driven not by curiosity but by necessity. The Blackbody problem would not let him rest. He wanted to believe that nature followed continuous laws, but the data demanded otherwise. Each curve on the graph seemed to whisper a secret he could not yet translate. It was as though light itself was trying to tell humanity that it possessed a deeper structure, something more fundamental than waves, something quantized, indivisible, and new. The drama of that period was not merely scientific, it was human. In laboratories across Europe, young researchers argued passionately about the meaning of the data. Could there be limits to classical reasoning? Was energy really continuous, or was there some hidden granularity waiting to be revealed? Planck listened but stayed silent. He was too careful to speculate, too disciplined to proclaim theories without proof. Yet in his quiet persistence, he was slowly drawing closer to the truth. The Blackbody mystery, once an obscure problem in thermal radiation, was about to ignite a revolution in science. By the end of 1900, the pieces were nearly in place. Planck's new formula fit every observation perfectly, and he had derived it from a bold new assumption about the quantization of energy. The world did not yet understand what he had done, nor did Planck himself foresee the magnitude of its consequences. But history would later mark that year as the birth of quantum theory, the moment when the smooth, continuous world of classical physics gave way to a universe built from invisible, vibrating quanta. In that transition lay the resolution of the Blackbody riddle, and the beginning of a new era in human understanding. The glow of a heated object was no longer just a color change, it was a message from the atomic world, revealing that light and energy followed rules unlike any the human mind had imagined. And though Planck did not know it yet, his reluctant step into the unknown had already changed the future of science forever. Planck's formula was born quietly, without the fanfare of revolution. There were no bold proclamations, no dramatic announcements that the old order of physics had fallen. To those who heard his 1900 lecture in Berlin, it seemed a minor technical correction to a difficult problem, an improvement in fitting experimental data. But beneath that calm exterior, a silent earthquake had begun. The very foundations of scientific thought had shifted. Energy, the most fundamental concept in all of physics, was no longer smooth and continuous. It came in tiny, indivisible packets. The universe, it turned out, was not a symphony of endless waves, but a dance of discrete notes. To grasp the magnitude of this discovery, one must first understand how deeply the idea of continuity was woven into the scientific worldview. Classical physics, from Newton to Maxwell, rested on the belief that nature could be described by continuous quantities. Motion, force, heat, light, all were thought to vary smoothly, infinitely divisible, without smallest parts. The mathematics of calculus reflected this philosophy. Every equation described a world that flowed without interruption. The notion that something as fundamental as energy could exist in chunks seemed absurd, even unscientific. Yet the Blackbody radiation data left no alternative. Nature herself was defying continuity. For Planck, the revelation came with both awe and discomfort. He later wrote that he viewed the quantization hypothesis as a purely formal assumption, a mathematical necessity, rather than a literal description of reality. But as time went on, the evidence became overwhelming. Other physicists began to test the implications of his law in different contexts. They found that it predicted not only the radiation curves of heated objects, but also the behavior of light in the photoelectric effect, the specific heats of solids, and even the emission of atoms. Everywhere it was applied. The quantum formula worked. The more the scientific community tried to treat it as a mere trick, the more it proved to be truth. Meanwhile, experiments in optics and electricity were uncovering new mysteries. When light struck certain metals, it ejected electrons, a phenomenon called the photoelectric effect. Classical wave theory could not explain why light of low frequency, no matter how intense, failed to release electrons, while light of higher frequency succeeded instantly. Planck's quantum idea provided the missing key. It suggested that light itself consisted of quanta, later called photons, each carrying energy proportional to its frequency, E equal to h nu. It was Albert Einstein, in 1905, who boldly applied Planck's hypothesis to light itself and showed that this particle-like behavior explained the photoelectric effect perfectly. In doing so, he extended Planck's reluctant step into a full-fledged quantum reality. The world was beginning to realize that Planck's constant, h, was more than a number. It was the measure of the universe's smallest heartbeat. It marked the scale at which the smooth waves of classical physics broke into discrete pulses. This constant appeared everywhere light and matter interacted. It governed the energy of photons, the vibration of atoms, and later, the uncertainty of position and momentum in quantum mechanics. What Planck had discovered, almost by accident, was the foundation stone of a new physics, one that would redefine not only science but philosophy itself. The Blackbody problem had thus opened a door no one could close. It led physicists to see that the microscopic world operates under rules entirely different from those of our everyday experience. In this new world, energy jumps in steps, particles behave like waves, and certainty dissolves into probability. The deterministic cosmos of Newton gave way to a universe woven with chance and possibility. It was as if light itself had whispered its secret to Planck, that the fabric of reality was quantized, built from pulses of energy too small to see but too powerful to ignore. At first, many scientists resisted the idea. They admired Planck's mathematical success but refused to accept his interpretation. Even Planck himself clung to the hope that someone might find a classical explanation that would preserve the old worldview. But the tide of evidence grew. When Einstein's photoelectric equation was confirmed experimentally, when Niels Bohr applied quantization to the orbits of electrons in atoms, and when the spectral lines of hydrogen were explained at last, it became clear that the quantum was not a temporary patch. It was the language of the universe. Yet to appreciate how far-reaching Planck's insight was, one must remember its origin. He did not set out to create quantum physics. He wanted to solve a single stubborn problem, but by following the data where it led, he uncovered something deeper, a principle that governed not just light, but all energy, all matter, all existence. That is the essence of scientific discovery, the willingness to see beyond what one expects, to let nature reveal her own laws even when they contradict human intuition. Planck had done precisely that. In the decades that followed, the concept of quantization evolved from a daring hypothesis into the foundation of modern technology. The equation E equal to hnu became the cornerstone of spectroscopy, lasers, semiconductors, and even quantum computing. Every time a photon is emitted from an LED, Every time an electron jumps between atomic levels, Planck's discovery is at work. The world that seemed abstract and theoretical in 1900 has become the practical backbone of our civilization. But to reach that point, scientists first had to accept that energy, the very breath of nature, behaves in a way no classical law could predict. In his later years, Planck often reflected on the path that led him there. He saw himself as a reluctant revolutionary. He had never sought to destroy classical physics but to complete it. In his modest office, he once said that he had tried for years to fit his data within the framework of traditional laws, but that nature would not allow it. I was forced, he said, to assume that energy could only be emitted in finite quanta. That single concession to reality changed everything. It was the moment when observation triumphed over ideology, when humility before nature gave birth to a new science. Meanwhile, the philosophical implications began to sink in. If energy was quantized, then continuity was an illusion. Between each quantum jump lay a silence, a pause in which nature waited for the next step. The universe was not a smooth flow but a sequence of pulses, like the ticking of a cosmic clock. Every atom, every photon, every vibration of light followed this rhythm, and if that was true, then even time and space themselves might not be continuous, but built from discrete intervals. A thought that continues to inspire physicists to this day. The mystery that began with the color of heated metal thus reached into the heart of existence. The glow of a furnace, the shimmer of starlight, the warmth of the sun, all revealed the same hidden structure. Energy released in packets, each tied to a specific frequency by Planck's constant. The Blackbody problem was not merely solved, it had been transformed into a revelation about the nature of light and matter. The secret energy of light, once invisible, now stood exposed as the fundamental building block of reality. What makes this story so extraordinary is that it began with failure, with equations that did not work, with data that refused to fit, with scientists frustrated by paradox. Progress came not from certainty but from doubt, not from victory but from surrender. Planck had to abandon the cherished belief in continuity to see the truth. His genius lay not in knowing the answer from the start, but in recognizing that nature's behavior was worth more than human preference. That act of intellectual humility was the spark that ignited quantum theory. As the 20th century unfolded, the consequences of that spark spread across science. Bohr's atomic model, Einstein's photons, Heisenberg's uncertainty, Schrödinger's waves, all traced their lineage to Planck's quanta. The world of the very small, once invisible, became the stage on which the universe's deepest laws played out. The stars themselves, shining with light born in quantum transitions, testified to the universality of Planck's discovery. Each flicker of a candle, each beam of sunlight, each electronic device that powers modern life is a tribute to the insight that energy is quantized. Even today, more than a century later, physicists continue to wrestle with the meaning of Planck's discovery. Quantum mechanics has grown into the most successful theory in all of science, predicting outcomes with staggering precision, yet its interpretation remains mysterious. Does the quantization of energy imply that reality itself is digital at its core? Is the universe, in some sense, made of information rather than matter? These questions all trace back to the same moment in 1900, when a quiet German physicist dared to suggest that energy comes in discrete packets. The riddle of blackbody radiation was solved, but in doing so, a new and deeper mystery was born. The mystery of quantum reality itself. To visualize how profound this transformation was, imagine the laboratory where it began, the air thick with the smell of heated metal, instruments gleaming under gaslight, graphs drawn by hand with meticulous care. In those lines and numbers, Planck saw something the world had missed, a message encoded in light. It told him that the energy of radiation increased not continuously but in steps, like rungs on an invisible ladder. Each rung corresponded to a quantum of energy, HNU, and each quantum represented a fundamental unit of interaction between matter and light. It was as if the universe had been playing a melody all along, but only now had humanity learned to hear its individual notes. The story of blackbody radiation is therefore not just the tale of a scientific puzzle, but the chronicle of a turning point in human thought. It marks the boundary between two eras, the age of certainty and the age of quantum mystery. Before Planck, physics sought perfection in smoothness and continuity. After Planck, it found truth in discreteness and probability. The light that once seemed uniform was revealed to be a mosaic of quanta, each carrying its own precise packet of energy. In the end, the enigma that haunted 19th century physics became the seed of 20th century progress. The ultraviolet catastrophe, once a symbol of failure, transformed into the gateway to quantum theory. The same equations that once led to infinity now led to insight. Through the Blackbody problem, nature had forced humanity to rethink what it means to understand her laws. She had shown that even the simplest phenomena, the glow of heat, the shimmer of light, could conceal the deepest truths. Max Planck's discovery of the secret energy of light began with a single question: why does a heated body glow as it does? The answer unveiled the quantized heart of the cosmos. It revealed that light is not a continuous wave, but a cascade of energy quanta, each born from the vibration of matter. That realization shattered the old universe and gave birth to a new one, a universe where energy, matter, and light are bound together by the rhythm of the quantum. Even now, when we look at a glowing ember, a shining filament, or the rising sun, we are seeing the legacy of that discovery. Each photon that reaches our eyes carries with it the signature of Planck's constant, the mark of quantization, the echo of that fateful moment when humanity first glimpsed the true nature of light. The mystery that began in the laboratories of Berlin has become the foundation of our understanding of everything from atoms to galaxies. The Blackbody problem was solved, but in doing so, it revealed the soul of physics, the quantized, radiant, eternal, secret energy of light. At the dawn of the 20th century, Max Planck found himself in a quiet but relentless battle against one of the most perplexing problems in physics. The Blackbody radiation curves had defied every attempt to explain them, and yet they were among the most accurate experimental results in all of science. Every laboratory in Europe could reproduce them. Every prism and detector confirmed their shape. The spectrum of light emitted by a heated object, measured in the dark rooms of Berlin and Munich, followed a mysterious pattern that no equation could capture. To Planck, a man who believed in the rational harmony of the universe, this was unbearable. If nature behaved with such mathematical precision, then there must exist a law, clear, elegant, and universal, that governed this radiation. Finding that law became his mission, a quest that would consume his thoughts and redefine the meaning of energy itself. Planck was not a revolutionary by nature. His temperament leaned toward caution, precision, and respect for the existing order of science. He admired the great architects of classical physics, Newton, Maxwell, and Helmholtz. And he sought continuity, not chaos, but the Blackbody problem was not a question that allowed comfort or complacency. It demanded boldness. In the quiet of his Berlin study, surrounded by stacks of mathematical papers and data sheets, Planck felt the growing tension between the old world of physics and the unexplainable behavior of light. His colleagues debated the issue endlessly, yet none could see a way out. Some dismissed the problem as unimportant. Others believed the answer must lie in unknown mechanical processes within matter, but for Planck, it was personal. He could not accept that a phenomenon so fundamental, the emission of light and heat, could elude the grasp of reason. He began by reviewing everything that was known. The experimental work of Heinrich Rubens and Ferdinand Kirlbaum provided him with precise measurements of the radiation intensity across wavelengths and temperatures. Rubens, a meticulous experimentalist, was among Planck's closest collaborators. The two men often met in the evenings, comparing theoretical predictions with laboratory results. Rubens's instruments, finely tuned to detect even the faintest infrared emissions, had revealed with astonishing accuracy how the intensity of radiation rose, peaked, and then fell as wavelength changed. Each curve was a signature of nature, a fingerprint of light's secret structure. Planck studied these curves as a musician studies a score, searching for the mathematical rhythm that tied them together. He knew that any valid law must connect three variables: the wavelength or frequency of radiation, the temperature of the emitting body, and the intensity of energy at each point. Classical physics offered partial answers. At long wavelengths, the Rayleigh-Jeans law seemed to fit. At short wavelengths, Wien's law worked reasonably well. But between these regions lay chaos. The true curve bent smoothly, while the equations either diverged or collapsed. Planck's goal was not to patch these theories together with empirical tricks, but to derive a single law that worked for all conditions, a universal radiation law. For months he filled his notebooks with equations, trying to express the behavior of energy as a continuous function of frequency and temperature. He used the principles of thermodynamics, statistical mechanics, and electromagnetic theory, adjusting variables and constants in search of harmony. Yet every attempt failed. The mathematics either overshot the data or undershot it. At high frequencies, energy rose to infinity. At low frequencies, it vanished too soon. The equations refused to meet nature's line. It was as if light itself was mocking human intellect, dancing just beyond the reach of reason. Still, Planck refused to give up. He believed, with almost spiritual conviction, that the laws of nature were absolute and discoverable. He often said that science was not about inventing truths, but about uncovering the order already woven into the universe. Somewhere, hidden behind the chaos of numbers, there had to be a principle that united all these curves into one coherent formula. He began to suspect that the answer lay not in modifying existing laws, but in questioning the very foundation of how energy was distributed among the microscopic oscillators that emitted radiation. He visualized the blackbody as a cavity filled with countless vibrating charges, oscillators that absorbed and emitted electromagnetic waves. These oscillators existed at different frequencies, and their combined behavior determined the radiation spectrum. In classical physics, the energy of each oscillator was thought to vary continuously. That assumption, however, was precisely what led to the ultraviolet catastrophe. If energy could take on any value, then at high frequencies, there would be an infinite number of ways to distribute it, and hence infinite total energy. Something about that assumption was wrong. Yet Planck hesitated to discard it. Continuity was sacred. The idea that energy could be quantized had not yet even formed in his mind. Instead, he tried to find a mathematical expression that would make the old theory behave better. He worked tirelessly, deriving relationships between entropy and energy, between frequency and temperature, between microscopic and macroscopic states. Each evening he compared his results with Rubens's data, and each time he found some improvement but never perfection. The fit was always slightly off, the theory always lagging behind the truth. Then came a breakthrough of intuition. Planck noticed that at high frequencies, the data matched Wien's law closely, but at low frequencies, it followed the Rayleigh-Jeans trend. Perhaps the true law bridged the two, combining their strengths. On October 19, 1900, after one of his late-night discussions with Rubens, Planck sat at his desk, pencil trembling in hand, and began to test a new formula, one that contained elements of both existing laws, but introduced an exponential factor to control the growth of energy at short wavelengths. When he plotted it against Rubens's latest data, the match was perfect. For the first time, a single equation described the entire radiation curve from infrared to ultraviolet. It was elegant, precise, and eerily beautiful. Planck could scarcely believe what he saw. But success brought no peace. A perfect fit was one thing, a physical explanation was another. Planck could not rest until he understood why his formula worked. He began to dissect it, tracing each mathematical term back to its possible physical meaning. That search led him to a terrifying realization. The only way to derive his formula from first principles was to assume that the energy of the oscillators could not vary continuously, but only in discrete amounts, integer multiples of a small constant multiplied by the frequency, energy in other words, came in steps. At first, Planck resisted the idea. It was too radical, too unlike anything in classical science, but the equations demanded it. To make the mathematics align with the data, he had to assume that each oscillator could emit or absorb energy only in specific quanta, not in an unbroken flow. He treated this assumption as a purely formal device, a mathematical fiction introduced to make the numbers work. Yet deep down, he knew that such mathematical tricks often pointed toward deeper truths. The pattern was too perfect to be coincidence. He called the proportionality constant h, later known as Planck's constant. Its value was unimaginably small. roughly 6.626 10^34 joule seconds, but it carried cosmic weight. It defined the smallest possible action in the universe, the fundamental unit connecting energy and frequency. The equation E equal to hnu was born quietly, almost reluctantly, from the margins of his derivation. Planck realized that this tiny constant governed the scale at which the continuous world of classical physics gave way to the granular world of atoms and radiation. To those who heard him present his findings to the German Physical Society on December 14, 1900, it sounded like a modest technical achievement. Planck himself introduced it humbly, calling it an act of desperation. He was not claiming to have discovered a new theory of nature, merely a formula that worked, but history would later mark that day as the birth of quantum theory. The simple desire to find a mathematical law for blackbody radiation had opened a doorway into the quantum universe. Planck's quest was not merely mathematical, it was philosophical. He was searching for order in a world that appeared disordered, for simplicity within complexity. His belief in the unity of nature was unshakable. Every number, every curve, every term in his equation had to correspond to a physical truth. That was his guiding principle. He did not invent laws, he revealed them. The blackbody problem, in his eyes, was a window into something universal, a principle that governed both the smallest particles and the grandest stars. Yet in those early days, he did not fully grasp what he had unleashed. He continued to hope that someday someone would find a classical explanation for his law, one that would preserve the continuity of energy. But the tide of evidence was turning against him. Einstein's work on the photoelectric effect, Bohr's atomic model, and the subsequent discoveries of quantum mechanics all trace their roots to that one daring assumption. Planck's modest mathematical law had become the foundation of a new worldview. Looking back, one can sense the drama of his intellectual journey. Imagine Planck in his study, the lamplight flickering over pages filled with equations, the silence broken only by the scratching of his pen. Outside, Berlin's winter air carried the faint sounds of a changing century: carriages, telegraphs, electric lights, symbols of human progress, powered by the very energy he sought to understand. Inside, one man wrestled with the invisible structure of light, trying to capture its secret in the language of mathematics. It was not an experiment that led him there, nor a flash of inspiration, but relentless reasoning guided by faith in the order of nature. Every scientist faces a moment when logic and intuition diverge, when the known rules fail, and only imagination remains. For Planck, that moment arrived when he dared to let the mathematics lead him beyond the comfortable boundaries of classical physics. His faith was not in his own brilliance, but in nature's consistency. If the universe appeared paradoxical, it was only because human understanding was incomplete. The law he discovered was not the product of rebellion, but of obedience to truth. Even when it defied tradition, Planck's quest did not end with his discovery, it only deepened. He spent years refining his ideas, exploring their implications, and teaching a new generation of physicists who would expand upon them. Many of his students, including Einstein and Schrödinger, would push the quantum concept far beyond what Planck himself imagined. Yet through it all, Planck remained humble. He often said that his discovery had come not through genius, but through persistence, through unending striving toward clarity. That striving defined his life's work. As the new century unfolded, the world began to change in ways Planck could not have foreseen. The equation he had derived to explain a simple thermal phenomenon would become the cornerstone of technologies that reshaped civilization, from electronics to lasers to quantum computers. But in 1900, none of that was visible. There was only a man, a blackboard, and a question that refused to die: what law governs the energy of light? For Planck, the search was never just about solving a problem, it was about restoring harmony to the language of physics. He believed that the universe was built on mathematical beauty, and he sought the equation that could reveal it. The blackbody radiation law was that revelation, the hidden melody of light, expressed through the constant H. In those silent moments when Planck stared at his graphs, watching the theoretical curve merge perfectly with experiment, he must have felt that he had touched something eternal, a truth that connected the human mind with the structure of creation itself. In the months following his discovery of the radiation law, Max Planck's days blurred into a single, long calculation. He had the formula that matched the data, but what still haunted him was why it worked. The curve itself was perfect, a smooth rise, a sharp peak, and a graceful fall. Yet the physics behind it remained an unsolved riddle. The experimentalists could measure light's intensity at every wavelength. Planck wanted the principle that would make sense of those numbers. His life had become a dialogue between mathematics and nature, between cold equations and the mysterious warmth of light. Each morning he arrived at his office at the University of Berlin, the same desk littered with notebooks, drafts, and letters from colleagues who still clung to classical explanations. He read their arguments carefully, but as he returned to his blackboard, the lines of chalk seemed to whisper otherwise. The curve of Blackbody radiation was too elegant to be a coincidence. Somewhere inside that graph lay a message about the true structure of energy. He could not yet see it, but he could feel it, as one feels the presence of a melody before hearing its notes. Planck began again from the foundations: heat, entropy, and probability. He recalled Ludwig Boltzmann's idea that entropy was a measure of the number of microscopic arrangements that could produce a macroscopic state. Boltzmann had written the now famous equation S equal to K log W, connecting order and disorder through mathematics. Planck had always respected Boltzmann, though he once considered his statistical interpretation of thermodynamics too speculative. But now, as he stared at his radiation data, Planck realized he might have to step into that same statistical world to find the key. The classical view, that energy changed continuously, was not enough. He needed a new way to count energy itself. He imagined his oscillators again, countless tiny resonators vibrating inside the walls of a blackbody cavity. If he could find out how these oscillators shared energy, he could explain the observed spectrum. The problem was purely mathematical, but its consequences reached into the heart of physics. Planck began dividing the total energy among the oscillators, not smoothly, but in small parcels. He did not yet believe in the physical existence of these quanta, but the mathematics demanded them. To apply Boltzmann's entropy formula, he had to assume that the energy of each oscillator could be split only into finite units, each of size nu. Without that assumption, the number of possible arrangements W would be infinite, and entropy would lose meaning. It was a daring step, one that Boltzmann himself had never taken. When Planck inserted it into his calculations, the mathematics finally made sense. Night after night he tested the result, comparing it with Rubens's newest measurements. The curves matched so precisely that Planck could hardly contain his excitement. He walked home through the dark Berlin streets, the winter air biting against his face, his mind racing faster than his footsteps. He knew that he had touched something fundamental. Energy could not be a continuous ocean. It was a sea of ripples, each one distinct, each one counted. He was not yet ready to say this aloud, but the realization filled him with both joy and unease. He was a conservative man who believed in stability and order, yet his mathematics was whispering a revolution. In December 1900, he stood before the German Physical Society and presented his law. His voice was calm, his words carefully chosen. He described how each oscillator emitted energy in discrete quantities proportional to its frequency, and how this assumption led to a perfect match with experiment. The audience listened politely, unaware that they were witnessing the birth of quantum physics. To them, it sounded like a clever refinement of thermodynamics, not a rewriting of nature. Planck himself barely grasped the magnitude of what he had done. He called his hypothesis a purely formal assumption, and even after the applause faded, he continued to hope that a classical explanation would someday appear. In the months that followed, Planck revisited his calculations repeatedly, searching for a way to reconcile them with the continuous world he had grown up believing in. But the more he tried, the clearer the truth became. Every physical phenomenon that involved light or heat seemed to echo the same quantized structure. The law worked not only for blackbodies, but for all kinds of radiating systems. It was as though the universe itself had been quantized, and Planck's constant h was its fundamental pulse. He began to notice the philosophical implications. If energy existed in discrete packets, then nature itself had a smallest possible action, a graininess woven into its fabric. It meant that determinism, the sacred pillar of classical physics, might not hold in the microscopic realm. Processes once thought continuous could only happen in jumps, transitions, not flows. To Planck, this was unsettling. He had spent his life believing that every effect followed smoothly from its cause. Now his own equations suggested a universe built on leaps of energy, not streams of continuity. He wrote to a friend that this discovery felt like an act of desperation, a reluctant surrender to the demands of mathematics. Still, he pressed on. The more deeply he explored, the more consistent the picture became. The constant H appeared everywhere he looked, a universal signature connecting the behavior of light, heat, and matter. It was small enough to be invisible in the macroscopic world, but dominant in the atomic realm. In that contrast lay the bridge between the two worlds. The familiar and the quantum. Planck had discovered the stepping stone that would allow later scientists to cross from classical certainty to modern uncertainty. By 1901, letters from other physicists began to arrive. Some congratulated him on his elegant solution, others expressed skepticism. Many simply didn't understand what he meant. Even Einstein, when he first read Planck's paper, sensed that something profound lurked behind it. Within 5 years, Einstein would extend Planck's idea to light itself, proposing that it consisted of quanta, photons, each carrying an energy. Knew that leap, building directly on Planck's mathematics, would confirm that the quantization was real, not just a mathematical convenience. But in 1900, Planck stood alone on the edge of a new world, aware that he had glimpsed the pattern, but unsure of the landscape it revealed. His daily life remained simple: lectures, family dinners, walks in the garden. Yet beneath that routine burned a quiet fire. He often pondered the relationship between science and faith, between mathematics and morality. To him, discovering a law of nature was an act of reverence, a way of glimpsing the mind of the Creator through logic and number. He never considered his quantum hypothesis an accident. He saw it as the inevitable outcome of nature's order. He wrote that the scientist's task is to read what is written in the book of nature, not to dictate what it should say. His equation had been dictated by the data, and he obeyed. As the years passed, others began to build upon his foundation. Niels Bohr used Planck's constant to explain the stability of atoms, showing that electrons could occupy only certain quantized orbits. Louis de Broglie extended the idea further, proposing that matter itself had wave properties defined by H. Werner Heisenberg and Erwin Schrödinger would later construct entire mathematical frameworks around that same constant. All of them traced their lineage back to Planck's search for a single radiation law. What began as one man's attempt to explain the glow of hot metal became the cornerstone of quantum mechanics. Looking back, it is astonishing how much of modern life rests on the outcome of that solitary struggle. The very technologies that illuminate cities and carry voices across oceans, lasers, transistors, solar cells, all depend on Planck's constant. Every photon emitted by an LED, every electronic transition in a computer chip obeys the equation E equal to hnu. The mathematical law Planck sought has become the operational law of civilization, yet at its heart remains the same mystery that drove him. Why does nature choose discreteness over continuity? Planck's notebooks from that era reveal the tension between faith in reason and the humility of discovery. On one page he scribbled calculations for entropy and probability. On another, personal reflections about the limits of human understanding. Science progresses, he wrote, not because we have the truth, but because we seek it. That relentless seeking defined him. He never glorified himself as a revolutionary. He saw his achievement as one step in the endless journey toward understanding, a journey that began long before him and would continue long after. In the quiet moments of his later years, Planck would sometimes recall the night he found the final form of his equation. He described it as a moment of serene clarity, a sudden alignment of logic and beauty. The numbers had fallen into place as though the universe itself had whispered the answer. It was not so much a discovery, he said once, as a surrender. He had stopped fighting the data and allowed it to guide him, even when it led away from everything he had believed. That surrender was the true act of genius. From that surrender came the mathematical law he had sought, simple, universal, and eternal. It described not only the spectrum of blackbody radiation, but the quantized rhythm of the cosmos. Each flicker of light, each vibration of energy, each atomic transition followed its rule. Planck's constant became a symbol of the hidden structure of reality, the smallest bridge between the measurable and the unknowable. When we look back at his journey, it is tempting to imagine it as a story of triumph, but for Planck it was a story of duty. He had not set out to change the world, he had set out to understand it. The blackbody problem had challenged him, and he responded with patience, precision, and faith in the harmony of mathematics. In doing so, he revealed that even light, that most ancient and familiar of phenomena, holds within it a secret pattern, a quantized pulse that underlies all existence. Today, when physicists speak of the quantum world, they speak the language that began with his quest. Every calculation that involves energy and frequency carries his constant, h, as its signature. It is the quiet reminder of the night when a man in Berlin found the equation that could explain the energy of light. That search, born of frustration and perseverance, became the turning point of modern science. The law he discovered still glows at the center of physics, as steady and unyielding as the blackbody itself, a mathematical flame that never fades, illuminating the path between the visible world and the invisible order that sustains it. When Max Planck finally dared to propose that energy could not flow continuously, he was stepping across a line that no physicist of his time had imagined could be crossed. For centuries, the idea of continuity had been sacred. Motion, force, light, everything seemed to unfold as a smooth, unbroken stream, perfectly described by calculus and geometry. Yet Planck's equations, born from the stubborn blackbody data, refused to obey that principle. They whispered a different truth, that nature advanced in steps, not slides, that energy itself came in indivisible quanta. To make sense of the glow of a heated object, he had to imagine the universe itself as granular. In his study, he often stared at the graphs Rubens had drawn, tracing the smooth bell-shaped curves with his finger, and wondered how something so continuous in appearance could come from a process that was not continuous at all. It was a paradox worthy of philosophy. The world looked seamless to the human eye, yet the mathematics said it was built from pulses. Every time an atom radiated light, it did so in a discrete burst, an energy packet whose size was determined by its frequency. Between those bursts, there was silence, a pause, a waiting. That was the meaning of his equation E equal to hn, though Planck himself was still uneasy admitting it. He had introduced the assumption reluctantly, almost apologetically. In his 1900 paper, he described it as a formal device, a mathematical trick to make the curve fit. But deep down, he knew that mathematics seldom lied about nature. Each time he recalculated the energy distribution, the same constant appeared. It was not an artifact of the method, it was a property of the universe. His colleagues did not yet grasp the significance. They saw only a new formula, not a new reality. To them, Planck's constant was just another adjustable number, like those in earlier empirical laws. But Planck sensed that he had touched the bedrock of physics, the smallest grain of action, the quantum of energy. He began to picture the oscillators in the blackbody cavity not as free emitters of any amount of energy, but as instruments playing notes at fixed intervals. Each could vibrate only by absorbing or releasing energy in multiples of hn. If an oscillator wanted to emit twice that amount, it had to jump 2 steps, not one continuous slide. The simplicity of the image astonished him. It explained why high-frequency light did not contribute infinite energy. Nature simply refused to let oscillators take fractional steps. The ultraviolet catastrophe vanished as if by magic. But it was not magic, it was quantization. To understand what a radical idea this was, one must recall how firmly 19th-century physics believed in determinism. Every motion could be predicted if the initial conditions were known. Energy flowed smoothly. Matter behaved like clockwork. The notion that energy could appear in sudden jumps seemed to violate the very spirit of science. Planck himself struggled to reconcile it with his own philosophy of natural law. He often compared the new picture to the structure of music. Continuous sound made from discrete vibrations. The ear hears a melody, not the individual frequencies. The mind perceives continuity, but underneath lies quantization. Slowly, the implications began to unfold in his thoughts. If light was emitted in quanta, then perhaps it was also absorbed that way. Each quantum of energy, once released, must travel as a unit. That meant that light, which everyone believed to be a continuous wave, might also have a particle-like character. The wave could carry the rhythm, but the energy rode in discrete packets. The boundary between particles and waves began to blur. Planck did not dare say it aloud, but the thought lingered. Somewhere in the nature of light, there was a duality waiting to be recognized. The more he worked, the more the constant H appeared to him as a threshold separating two worlds. On the large scale of human experience, where H is vanishingly small, energy seems continuous. On the atomic scale, where H matters, it comes in chunks. That explained why the quantum nature of light had remained hidden for so long. Only when scientists peered into the invisible realm of heat radiation did the discreteness reveal itself. The smooth world of the senses was merely an illusion, created by an unimaginably fine granularity. Just as a photograph appears smooth until one looks closely enough to see the pixels, so too did energy appear continuous until Planck resolved its grains. He began to test this idea mentally against other known phenomena: the colors of heated metals, the spectral lines of gases, the efficiency of incandescent lamps. All hinted at the same law. Every emission of light involved an atomic jump between quantized states. Every color corresponded to a particular frequency, and therefore to a particular quantum of energy. Nature was quantized not only in radiation but in matter itself. The unity of physics, which Planck so deeply cherished, was preserved, but in a new form. The harmony was still there, yet it was a harmony of discrete notes rather than continuous tones. The intellectual courage required to hold this view cannot be overstated. Planck was a man of principle and order, not of upheaval. He once said that new scientific truths do not triumph by convincing their opponents, but because their opponents eventually die. In his own lifetime, he watched as his reluctant assumption gave birth to a revolution that many of his contemporaries resisted. Yet he never claimed the role of a rebel. He saw himself as an interpreter, translating nature's language into mathematics. The discovery of quanta, he believed, was not his achievement alone. It was the revelation of a truth that had always existed. Late in the evenings, when his calculations were done, he would sit by the lamp and write notes about the philosophical meaning of his work. He wondered what it meant for the concept of continuity, for determinism, for the human understanding of cause and effect. If energy came in packets, could time and space themselves also be quantized? Were there smallest possible intervals of reality beyond which measurement lost meaning? Such questions filled his private reflections. He sensed that he had opened a door to a new realm, but he did not yet know where it led. To visualize his discovery, imagine a staircase bathed in light. Classical physics had believed that energy could move smoothly up the incline, like a ball rolling upward without interruption. Planck's quanta changed that image. The staircase had steps. Each step was separated by a fixed height corresponding to nu. To climb from one level to another required a specific quantum of energy. No half-steps were allowed. The universe, it turned out, did not glide. It hopped. Every atom, every photon, every vibration of matter moved in discrete transitions. The continuity perceived by the senses was the sum of countless jumps too small to see. This new vision of nature would eventually reshape everything from chemistry to cosmology. But at that moment, Planck saw only the first faint outlines. He was not alone for long. Einstein soon recognized that Planck's quanta could explain the photoelectric effect, proving that light itself behaved as if it were made of particles. Bohr used the same idea to describe electrons leaping between orbits in atoms. What began as a reluctant hypothesis turned into the cornerstone of a new physics. But in 1900, it was still Planck's private revelation, a quiet revolution carried on the tip of a constant no larger than a whisper. The beauty of the idea lay in its inevitability. No experiment forced it, no philosophical theory demanded it, it emerged naturally from the mathematics. When Planck followed the logic of entropy and probability, the quantization appeared as the only way to make sense of the numbers. It was as though the universe itself insisted on discreteness, and Planck had merely given it a name. The constant h was not a human invention. It was a cosmic signature, the smallest measure of action allowed in the world. Every vibration, every emission, every interaction carried multiples of that fundamental unit. To grasp its depth, one must imagine how it changed the relationship between matter and energy. In classical physics, energy could be divided infinitely without losing meaning. In Planck's world there was a floor, a smallest possible amount below which energy simply could not exist. That idea shattered centuries of continuous reasoning. It hinted that the universe was not an unbroken fabric, but a tapestry woven from individual threads of action. Even the laws of thermodynamics, once seen as purely macroscopic, found their roots in this microscopic quantization. Heat was no longer a vague flow. It was the collective hum of countless quanta exchanging energy. The philosophical shock was profound. The deterministic world of Laplace, in which a perfect intellect could predict all future events, began to crumble. If energy moved in discrete jumps, then between those jumps there might exist intervals of unpredictability. The seeds of uncertainty were planted. Planck did not explore them fully, but later generations would. Heisenberg, Schrödinger, and others would turn the quantum into a full-fledged theory of probabilities, where exact prediction gave way to statistical expectation. The line from Planck's quanta to quantum mechanics is direct and inevitable, a cascade of insights flowing from a single assumption. What made Planck's insight so enduring was its simplicity. The world is quantized. From that sentence springs the modern age, the lasers that scan barcodes, the semiconductors that power computers, the atomic clocks that define time. All rely on quanta. Every piece of modern technology carries the echo of Planck's realization. Yet he never sought such outcomes. He was not chasing innovation, he was chasing understanding. His quanta were not inventions but revelations, glimpses of how nature truly behaves. In his lifetime, Planck often faced skepticism. Some of his peers called the idea metaphysical, others dismissed it as temporary, but the evidence kept growing. Spectroscopy, photoelectric measurements, specific heats, all confirmed the quantized nature of energy. One by one, the defenders of continuity conceded. The universe, they realized, was not the smooth machine they had imagined, but a symphony of pulses, each note separated by the rhythm of ch. As the idea matured, Planck's discomfort slowly turned into quiet acceptance. He began to see quantization not as a violation of nature's harmony, but as its refinement. The discreteness of energy was itself a kind of order, a hidden architecture beneath the apparent flow. Just as a mosaic reveals its beauty through the arrangement of its tiny tiles, the universe revealed its structure through the arrangement of its quanta. The harmony was deeper than anyone had guessed. Continuity had not been destroyed. It had been composed from discontinuity. Planck's revolutionary assumption changed more than physics. It changed the human conception of reality. It taught scientists that nature does not conform to human expectation but to its own laws, however strange. It revealed that the invisible world could obey rules utterly alien to common sense yet perfectly consistent with observation. It showed that truth could hide not in grand theories but in constants so small that they seemed trivial. Out of that smallness came the greatest transformation of thought since Newton. Even now, every time light flickers, every time an electron transitions, every time energy changes form, Planck's quanta are at work. The universe continues to operate by the rule he uncovered. Energy is not continuous. It moves in discrete, indivisible packets. That single assumption, made in a quiet office by a man seeking only to fit a curve, became the foundation on which modern physics stands. Planck's assumption that energy came in discrete quanta was like a spark thrown into a forest of ideas waiting to ignite. In the years that followed his announcement, that spark began to spread, quietly at first, then uncontrollably, until it transformed the very landscape of physics. What he had meant as a mathematical convenience started to reveal itself as a universal principle. The classical picture of a smooth, predictable universe began to flicker under the new quantum light. Energy was no longer a continuous current, but a succession of pulses, each one separated by the immutable rhythm of Planck's constant. The revolution had begun, and it carried within it the seeds of every modern technology and theory that would come after. Planck's personal struggle with the meaning of this discovery remained intense. He did not see himself as a revolutionary, nor did he relish the role. To him, the quantization of energy was a necessity forced upon him by the stubbornness of experimental data. He had not set out to overthrow classical physics. He had set out to save it. Yet the more he tried to reconcile the two worlds, the more he realized that the quantum idea refused to fit into the old order. Nature had drawn a new boundary, and he had no choice but to cross it. In his letters he described how the conclusion seemed to come against his own will, as though he had been led there by the logic of mathematics rather than by choice. His humility became part of his strength. Where others might have resisted, he obeyed the evidence. The true depth of Planck's quantum began to emerge as others tested it. The most dramatic early confirmation came from Albert Einstein, who in 1905 applied the concept to light itself. Einstein proposed that the energy packets Planck had imagined for the oscillators were not just an internal bookkeeping device, but a real property of light. He called them light quanta, what we now call photons. Each photon, Einstein said, carried an energy equal to hn, exactly as Planck's equation described. With that simple extension, the photoelectric effect, which had baffled physicists for decades, suddenly made sense. When light struck a metal surface, electrons were ejected only if the light's frequency was high enough to deliver a single quantum of energy sufficient to free them. No amount of low-frequency light could substitute for that minimum quantum. Energy was not cumulative, it was quantized. Planck at first resisted Einstein's interpretation. He still believed that light was fundamentally a wave, continuous and spread out, not a collection of particles. The idea of photons seemed too drastic, yet even his reluctance could not change the growing mountain of evidence. Each new experiment confirmed the quantized nature of energy transfer. The quantum was not just a mathematical fiction, it was the fabric of reality. Planck's constant h had become the symbol of a new kind of law, one that governed the invisible interactions at the heart of matter. In those early years, few understood how revolutionary this was. The old physics had given humanity confidence that the universe could be fully known through deterministic laws. Planck's quanta, small though they were, shattered that illusion. They implied that nature operates with inherent limits. The smallest possible energy exchange, the smallest possible action, the smallest possible step between two states. Beneath the smoothness of light and heat lay a grainy structure that set the scale for everything else. It was as if the cosmos had a built-in resolution, a fundamental pixel size below which no detail existed. The continuous film of reality was actually made of discrete frames. Planck's insight reached far beyond blackbody radiation. It began to explain why atoms are stable, why they emit light in discrete spectral lines, why chemical reactions release specific amounts of energy. Without quantization, electrons would spiral into nuclei and matter would collapse. With it, nature's architecture became comprehensible. The tiny, indivisible quantum served as a unit of cosmic order. In the space of a few years, Planck's reluctant assumption transformed into a universal constant appearing in every equation of modern physics. From quantum mechanics to quantum field theory, from relativity to cosmology, the symbol H stands as a reminder of that first moment of insight. To the scientific community, however, acceptance came slowly. Many older physicists could not believe that energy might come in packets. They argued that the classical wave theory had been too successful to abandon. Debates raged in lecture halls and journals. Was Planck's quantum a real thing, or just a mathematical convenience? Did atoms truly jump between energy levels, or was that language merely symbolic? Each year brought new experiments that tilted the balance toward reality. The spectral lines of hydrogen, once mysterious, could now be calculated precisely using quantized orbits. X-ray emission and absorption, the heat capacities of solids, even the color of starlight, all spoke the same language. Step by step, the world began to think in quanta. Through it all, Planck maintained a quiet dignity. He did not seek fame or credit. He often referred to his discovery as a lucky guess or an unavoidable conclusion. Yet he also understood its profundity. The assumption that energy consists of finite elements, he wrote, proves to be the only one which leads to the correct radiation law. That sentence, modest in tone, marks the turning point of scientific history. It was the first open acknowledgement that continuity was an illusion, that reality was built from discrete quanta of energy. The line dividing the classical and quantum worlds had been drawn. As the implications spread, the idea of quantization began to seep into other fields. In chemistry, it explained why atoms form stable molecules and why chemical reactions release specific quanta of energy, as heat or light. In astronomy, it shaped the understanding of how stars emit radiation and how their temperatures can be measured. In electronics, it laid the groundwork for the discovery of semiconductors and transistors. Each application traced back to that same principle. Energy is not continuous. It comes in indivisible packets, and those packets govern everything from the glow of a candle to the fusion in the heart of the sun. The philosophical implications were equally vast. If nature operates in quanta, then the universe is not infinitely divisible. There exists a fundamental limit to measurement, a smallest action that defines the boundary between what can be known and what can only be inferred. That realization would later mature into Heisenberg's uncertainty principle and the probabilistic interpretation of quantum mechanics. But its seed was in Planck's quanta. The assumption that energy changes in finite steps opened the door to a world where certainty itself would be quantized. The cosmos, once imagined as a perfect machine, revealed itself as a tapestry woven from probabilities and discrete events. Planck lived to see his idea grow into a revolution, though he remained cautious to the end. He admired the work of the younger physicists, Einstein, Bohr, Schrödinger, Heisenberg, but he never fully accepted the abandonment of determinism. To him, quantization was a law of nature, but not a license for randomness. He believed that behind the apparent uncertainty lay an ultimate order that humans could someday grasp. In that conviction, he remained both a man of science and a man of faith. His discovery had changed the world, but his humility kept him grounded. "I did not seek revolution," he once said, "it found me." In the years after World War I, as Germany struggled through hardship, Planck continued to teach, to write, and to reflect. His lectures often returned to the theme of harmony, the idea that even the most shocking discoveries ultimately fit into a greater order. He would explain to his students how the quanta, though strange, restored balance to physics by resolving contradictions that had plagued it. The ultraviolet catastrophe, the failure of classical theories, all were healed by the assumption of discreteness. Nature, he said, is subtle but never malicious. It hides its secrets not to deceive but to invite deeper inquiry. As technology advanced, the tangible proof of his theory surrounded him. The first quantum devices appeared: photoelectric sensors, X-ray tubes, atomic clocks. Each one relied on the principle he had uncovered decades earlier. Every new success reminded the world that Planck's quanta were not abstractions but realities, embedded in the machinery of modern life. Even when the language of physics grew more abstract, when Schrödinger spoke of wave functions and Heisenberg of matrices, Planck's constant remained the bridge between mathematics and the measurable world. It was the heartbeat of quantum theory. The beauty of Planck's insight lay in its universality. It did not depend on specific materials, conditions, or phenomena. It applied equally to the radiation of stars and to the emission of atoms, to the flicker of a candle and the glow of a galaxy. Everywhere energy moved, it did so in quanta. That universality gave physicists the confidence to build an entirely new framework of thought, one that would eventually explain superconductivity, nuclear reactions, and the structure of space-time itself. The smallness of H belied its grandeur. Within that tiny constant lay the blueprint of the cosmos. When we imagine Planck in his final years, we can see him as the quiet patriarch of a scientific family that had outgrown him. His students and their students were now reshaping the world with quantum mechanics, relativity, and atomic energy. Yet he remained the moral center, reminding them that science is not merely the conquest of knowledge but the pursuit of truth. He had seen how a single assumption, born from patience and obedience to data, could unlock the hidden order of creation. His life became a testament to the idea that great revolutions often begin not with bold proclamations, but with quiet realizations. Today, every photon that strikes a solar panel, every quantum bit in a computer, every atomic clock that measures time with unimaginable precision carries Planck's legacy. The concept of the quantum has transcended physics. It has become a metaphor for all discovery, tiny steps that produce vast consequences. The universe we now explore, from the smallest particles to the largest galaxies, dances to the rhythm set by his constant, E=hnu, is more than an equation. It is the signature of reality itself. From the darkness of a laboratory in Berlin, where a lone physicist sought a mathematical law for light, emerged the recognition that the universe itself is quantized. Energy, once imagined as a continuous ocean, revealed its true nature as a series of waves and steps, each one distinct, each one finite. Planck's assumption reshaped science, technology, and philosophy. It marked the end of the classical age and the dawn of the quantum era. And though he could never have foreseen all that would follow, Max Planck's simple, reluctant idea that energy comes in tiny, indivisible packets remains the foundation on which our understanding of the universe stands. When Planck introduced his daring idea that energy existed in discrete packets, he had unknowingly set into motion a scientific revolution that would break the very foundations of classical physics. For over 2 centuries, scientists had believed that the universe operated like a flawless clock, every motion predictable, every cause leading smoothly to its effect. Light was thought to be an undivided wave, spreading through space in continuous ripples of electromagnetic energy. But Planck's hypothesis shattered that comfort. By declaring that energy could only be emitted or absorbed in multiples of hnu, he had shown that the elegant equations of classical physics were no longer enough to describe reality. The certainty that had guided Newton, Maxwell, and Kelvin began to dissolve, replaced by a new vision of a universe built from invisible jumps and quanta. At first, the scientific community treated Planck's formula as a curiosity, an isolated solution to a difficult problem, but as other experiments confirmed his ideas, the true magnitude of what he had done began to emerge. His theory meant that the energy of light depended on its frequency, not its brightness, a concept that directly contradicted classical wave theory. Einstein soon took this principle and proved that light behaved not only as a wave, but also as a stream of particles, photons, each carrying a quantum of energy. The dual nature of light was born. In that instant, Planck's quiet equation became the cornerstone of a new science, quantum physics. It explained mysteries that classical theory could not: the photoelectric effect, the emission of atoms, the structure of matter itself. Every atom, every spark, every flash of light now told the same story. The universe was quantized. The break with classical physics was more than mathematical, it was philosophical. The old laws had promised a world of certainty. If one knew the initial conditions of any system, one could predict its future with absolute precision, but the quantum world defied such logic. It revealed a universe that worked in probabilities, where particles behaved like waves, and where observation itself could alter the outcome. Planck's discovery opened the door to that strange and beautiful reality. He himself did not explore its full consequences, but those who followed, Einstein, Bohr, Schrödinger, Heisenberg, built upon his foundation and redefined the meaning of reality. The atom was no longer a miniature solar system governed by deterministic orbits. It was a vibrating, probabilistic entity shaped by quantum laws. The impact of this revolution went far beyond physics. It changed how humanity understood existence itself. The discovery that energy comes in quanta suggested that the very fabric of the universe was made not of continuous threads but of countless tiny pulses of energy, like the beats of a cosmic heart. Space, time, and matter were revealed to be interwoven with uncertainty and chance, challenging centuries of belief in an orderly mechanical cosmos. The simple act of heating a piece of metal until it glowed had led to a profound truth. Beneath the apparent smoothness of reality lies a granular structure, a universe built on discrete exchanges of energy. Planck's law bridged two worlds, the visible and the invisible, the classical and the quantum. It explained why the color of a heated object shifts from red to white, why atoms emit specific wavelengths, and why energy cannot be divided infinitely. The formula that began as a desperate attempt to fit experimental data had become the key to understanding the entire structure of matter. It was the beginning of quantum mechanics, a science that would later give birth to electronics, lasers, semiconductors, and the digital age. Every light bulb, every computer chip, every satellite signal carries within it the legacy of Planck's constant. His discovery did not merely rewrite the equations of physics, it rewrote the human relationship with energy itself. Max Planck's breakthrough stands as one of the most profound turning points in scientific history. In solving the riddle of blackbody radiation, he had unknowingly dismantled the very framework of the old world and replaced it with something infinitely more mysterious. His constant, h, became the silent signature of the quantum realm, a bridge between the measurable and the unknowable. What began as an act of mathematical necessity became a revelation about the true nature of the universe, that all energy, all light, all matter exist not as a continuous flow but as countless tiny bursts of creation, each one a quantum leap toward understanding the fabric of existence. The equation E equal to h and u became the simplest yet most powerful bridge between the unseen world of atoms and the vast structure of the cosmos. It was the moment when mathematics and nature shook hands. In that short expression, Planck captured the essence of light's hidden rhythm, a precise relationship between energy and frequency, bound together by his constant h. This single formula revealed that every vibration of light, every photon traveling through space, carries a fixed amount of energy directly proportional to its frequency. It was a revelation that turned light from a continuous wave into a messenger of quantized truth, transforming the way physicists understood the universe. What seemed like an abstract mathematical curiosity soon became the cornerstone of all modern physics, linking the microscopic and the cosmic in a harmony that still guides science today. When Planck derived E equal to h and u, he could not have foreseen how it would echo through the next century. At its heart lay a profound idea: the higher the frequency of a wave, the greater its energy. This meant that blue light, with its shorter wavelength, carried more energy than red light, X-rays carried more still, and gamma rays, at the highest frequencies, carried energies powerful enough to alter matter itself. It explained not just why objects glowed differently when heated, but also how stars shone, how atoms interacted, and how energy flowed across the universe. This equation became the universal law of exchange between matter and radiation. It unified the behavior of everything that emits or absorbs light, from the smallest electron to the brightest star. Planck's constant h was tiny, but its importance was infinite. It set the scale for all quantum effects, defining the smallest possible action in nature. Without it, energy would blur into continuity again, and the universe would lose its quantized structure. This constant became a boundary line between two realms, the classical world of predictable motion and the quantum world of discrete phenomena. Every photon, every electron transition, every chemical bond obeyed that same proportionality. The constant was like the heartbeat of reality, quiet but everywhere, dictating the tempo of atomic motion and the frequency of light's vibration. In that number, 6.62, 6x10, 34 joule seconds, was encoded the fundamental rhythm of the cosmos. As physicists began to explore the consequences of E equal to h and u, they realized it described not only the energy of light, but the structure of all radiation and matter. It led Einstein to the concept of photons, Bohr to his model of the atom, and Schrödinger to his wave equation. Every major advance in 20th century physics carried Planck's constant in its heart. The photoelectric effect, X-ray emission, the stability of atoms, and even the uncertainty principle all grew from that relationship between energy and frequency. The world of the infinitely small had found its law, and that law could explain phenomena across the entire scale of existence. For the first time, scientists could measure the quantum structure of light and predict its behavior with astonishing precision. E=hnu also transformed technology and daily life. It was the foundation upon which the modern age of electronics, lasers, and communication systems was built. Every time a photon of light triggers a camera sensor, every time a microwave heats food, every time a satellite beam transmits a signal, Planck's equation is at work. The quantization of energy governs the functioning of transistors, LEDs, and solar cells. The constant that once seemed too small to matter has become the invisible architect of human progress. The quantum revolution it sparked has reshaped medicine, energy, and computation, turning Planck's quiet insight into a universal principle that powers the modern world. But beyond its scientific and technological consequences, the equation carried a deeper philosophical meaning. It suggested that nature, in its purest form, is both orderly and mysterious. Energy is not an unbroken river but a series of distinct drops, each one governed by a universal law. There is elegance in that discreteness, a rhythm so precise that even chaos obeys it. The universe speaks in quanta, and E=hnu is its grammar. Through that equation, humanity discovered that everything, from the flicker of a candle to the radiation of distant galaxies, follows the same fundamental rule. It united the vastness of the heavens with the minuteness of atoms, showing that the language of creation is mathematical, and that its alphabet begins with Planck's constant. Thus, in a few symbols, Max Planck revealed the secret harmony of energy and frequency. He transformed physics from the study of continuous waves to the science of discrete realities. The equation E=hnu was not just a formula, it was a revelation that energy itself has a heartbeat, a pulse that defines existence. It stands as one of the greatest expressions ever written by the human mind, a line of mathematics that captures the rhythm of the cosmos and whispers that even the light of the stars shines according to a law that began in the quiet study of one man searching for order in the glow of heated light. When Planck first introduced his theory, few realized how crucial experimental proof would be in transforming his idea from speculation into one of the most solid pillars of modern science. The beauty of his law lay in how perfectly it fit the data. Every wavelength, every temperature, every curve of blackbody radiation matched the predictions of his formula with uncanny precision. For decades, physicists had struggled with the mismatch between theory and experiment. Now, Planck's equation brought harmony where there had been contradiction. It was as if nature itself had nodded in approval, revealing that energy, when viewed through the lens of quantization, behaved exactly as his mathematics foretold. The very glow of heated matter became living evidence of a hidden order that no one had imagined before him. The experiments conducted by Heinrich Rubens and Ferdinand Kurlbaum at the Physikalische Technische Reichsanstalt were the foundation upon which Planck's revolution rested. Their precise measurements of radiation intensity across different wavelengths provided the map that Planck had been trying to decode. When Rubens handed him the latest data, showing how energy emission behaved at longer infrared wavelengths, Planck immediately saw the pattern that no other theory could explain. His formula fit perfectly, not approximately, not partially, but completely. It described the whole spectrum of light from the deepest red to the ultraviolet with mathematical grace. That moment was more than a scientific success. It was a revelation that the universe obeyed a quantized rhythm, measurable, predictable, and profoundly elegant. Other scientists soon began to test his equation in their own laboratories. In England, in France, and across Europe, experiments on heated metals, cavity radiation, and spectral lines confirmed the same result again and again. No matter how sensitive the instruments or how high the temperature, Planck's law remained unbroken. The ultraviolet catastrophe that had haunted classical theory disappeared as though it had never existed. What had once been a theoretical embarrassment became a triumph of precision. Every experiment that validated his formula deepened the realization that quantization was not a convenient mathematical trick, but a description of how nature truly operated. The quanta were real, and light, for all its apparent smoothness, carried energy in discrete packets. Einstein's explanation of the photoelectric effect provided perhaps the most dramatic experimental proof of all. Using Planck's concept of quantized energy, he demonstrated that light could eject electrons from a metal surface only if it carried photons of sufficient frequency, regardless of brightness. This simple but striking observation proved that energy transfer occurs in indivisible units, confirming Planck's original hypothesis beyond doubt. Suddenly, the theory was no longer confined to the mysterious domain of blackbody radiation. It had entered the tangible world of measurable effects. The photoelectric effect earned Einstein the Nobel Prize, but at its heart was Planck's constant, the invisible bridge between frequency and energy. The numbers matched perfectly, and physics was reborn. The experimental confirmation of Planck's theory reshaped scientific confidence. It taught researchers that mathematics could reveal truths that intuition might resist, and that even the smallest numerical constant could hold the key to cosmic order. The success of these tests inspired an entire generation of physicists to look deeper into the quantum world. Bohr used Planck's quantization to explain why electrons orbit the nucleus in fixed energy levels. Later, Schrödinger and Heisenberg would extend it to the motion of particles themselves, giving birth to quantum mechanics. Every step of that journey traced back to the first moment when experiment met theory in perfect symmetry, when Planck's formula and Rubens's data merged to form a single undeniable truth. The harmony between theory and experiment gave the quantum idea a solidity unmatched in the history of physics. Before Planck, energy had been an abstract continuum. After him, it became a countable, testable phenomenon. The flicker of a flame, the glow of a filament, the radiation of a star, all became laboratories of proof. Even today, experiments measuring atomic emission, laser frequencies, and cosmic background radiation continue to confirm the accuracy of Planck's law to an astonishing degree. It has never failed. The constant H is now known with incredible precision, defining not only energy but even the modern standard of measurement itself. From the simplest lab experiment to the farthest observation of starlight, every result agrees with the idea first confirmed by those early blackbody studies. What began as a desperate attempt to reconcile data with theory became one of the most empirically successful ideas in science. The quantum concept, once doubted, became undeniable because it worked. Flawlessly, repeatedly, universally, the consistency between experiment and prediction turned Planck's modest hypothesis into the foundation of modern physics. It was no longer the speculation of one man, but the shared discovery of humanity, proven in the glow of every heated object, in every spectrum of light across the sky. The experiments that confirmed it did more than validate a formula. They revealed a truth that transcended instruments, that even in its smallest actions, the universe is quantized, precise, and beautifully ordered. The impact of Max Planck's discovery did not end with the formulation of a new law or the validation of his equations. Its most profound legacy was the transformation it brought to the entire scientific world. Before Planck, physics had been a cathedral of certainty, elegant, ordered, predictable. Every motion, every wave, every flicker of light could, in principle, be calculated with perfect accuracy. But after Planck, that cathedral began to tremble. The quantization of energy did not merely solve a mathematical riddle, it unveiled a universe governed by hidden rules that defied human intuition. The discovery of quanta tore down the boundary between matter and radiation, between waves and particles, between the continuous and the discrete. It forced scientists to accept that the world they saw was not the smooth, deterministic machine they had imagined, but a tapestry woven from probabilities, vibrations, and limits. The birth of quantum theory was the birth of modern physics itself. Planck's constant H became the seed from which every new branch would grow. Einstein's relativity revealed that energy and mass were interchangeable. Bohr showed that electrons orbit atoms in quantized shells. Schrödinger described their motion as waves of probability. Heisenberg uncovered the limits of what could be known about position and momentum. Each discovery led back to Planck's quiet insight that energy was granular. The old picture of reality had been shattered, but in its fragments, scientists found new meaning. The universe was not less orderly, only more subtle. beneath the apparent chaos lay a mathematical beauty that linked all forms of matter and light in a single rhythmic language. That language shaped the 20th century. Quantum mechanics became the engine of technology, powering inventions that changed every aspect of human life, from the transistor to the laser, from medical imaging to nuclear energy, from the GPS and satellites to the quantum dots in modern screens. All trace their existence to Planck's quanta. Even the light that shines from distant galaxies, measured by astronomers to understand the origins of the universe, obeys his law. His constant defines not only the microscopic world, but also the very scale of the cosmos. It has become one of the fundamental parameters by which reality itself is measured. Through it, humanity gained the power to see and control energy on atomic scales, to harness light and matter in ways once thought impossible. But beyond its scientific and technological consequences, Planck's discovery carried a deeper philosophical weight. It redefined the relationship between humanity and the universe. It revealed that the smallest acts in nature, the emission of a photon, the vibration of an atom, are not infinite in variety but bound by precise steps, as if the cosmos were composed of musical notes. Each quantum of energy is a tone in the symphony of creation, and Planck's constant sets the pitch. The idea that everything, from light to life, unfolds according to quantized laws gave rise to a new vision of order, one in which uncertainty and precision coexist. The deterministic clockwork universe had given way to a probabilistic pulsating one, mysterious yet no less divine in its balance. In the years following Planck's death, quantum physics continued to grow, reaching into every corner of science. The discovery of quantum fields revealed that even empty space teems with energy, fluctuating according to Planck's constant. The birth of quantum electrodynamics and quantum computing showed that the universe operates like a vast processor, exchanging information in discrete units of energy. Planck's idea became not just a law of physics, but a philosophy of existence, that reality in all its complexity is quantized. Each discovery since then, from the Higgs boson to the entanglement of particles, has been a reaffirmation of his insight. The influence of Planck's work is so vast that it is impossible to separate it from the modern world. The technologies that shape daily life, the theories that explain stars and atoms, and the principles that define knowledge itself all flow from his equation. The quantum theory that began with the glow of a heated object now governs our understanding of black holes, of time, and of the origin of the universe. Planck had set out to solve a small problem, but he ended up revealing a new dimension of reality. His discovery reshaped not only physics, but the human imagination, showing that even the smallest constant could change everything. In the end, the legacy of Max Planck's discovery is not just scientific but eternal. It stands as a reminder that truth often hides in simplicity, that the universe yields its secrets not to those who demand them, but to those who listen with humility. Planck had listened, to data, to mathematics, to the quiet whisper of nature, and what he heard was the rhythm of light itself. Through that rhythm, humanity learned to see the invisible, to measure the immeasurable, and to glimpse the structure of reality at its most fundamental level. His discovery did more than revolutionize physics. It redefined what it means to understand the world, forever changing the way we perceive light, matter, and the infinite mystery that binds them together.